Good evening and welcome to our TI Technology webinar hosted by Texas Instruments Australia. We are excited to bring you Matrices, Unit 1, Topic 5 from the QCE Specialist Mathematics course with a very experienced mathematics teacher, lecturer and TI Technology user, Mr. Peter Flynn. My name is John Bowman and I am your host for this event. I teach mathematics to years 7 to 12 students at Lachlan Catholic College in Darwin, where I use TI technology to help students make stronger connections in their understanding of mathematics. But more importantly, I'm excited to introduce our panelist for today, Mr. Peter Flynn. Hi, Peter.
Hello, John.
Great to have you with us. Thank you for joining us. I'm always excited to learn a few things about what you know, and you know plenty about the Nspire. So thanks, Peter. As you can see, Peter has been a mathematics education teacher and lecturer for over 30 years in a variety of educational contexts. He has a rich knowledge of computer algebraic systems, called CAS as for short, as well as various examination boards. He is also the co-author of our recent QCE Mathematics Teacher Resource Booklet, as well as this week recently released Specialist Mathematics TRB. So thank you, Peter, for producing those. They are excellent documents that we can access online.
Thank you. Good evening, all. So what we're going to look at tonight is matrices from Unit 1. There's my email address if you wanted to follow up with some questions. And obviously, I'm Peter, as introduced by John. And if we have a look at our overview this evening, we're not going to do anything overly fancy. We're just going to concentrate really on some meat and potatoes functionality really from the TI-Nspire. But we're going to look at some matrix operation properties, in particular addition and multiplication. We're also going to look at the multiplicative identity and the multiplicative inverse. We'll look at determinants and inverses and finish up by looking at different ways in which we can solve matrix equations. And I'll focus in on systems of linear equations in two variables, x and y. So if we go to the next page, you'll notice across the top here, we got some tabs. So the first digit represents the problem number. So this is now problem 2, and the second digit represents the page number. So this is page 1 of problem 2. And what I've done here is I've used the Microsoft snipping tool. I've taken a screenshot from the Queensland Specialist Maths Teacher Resource book, which will be out soon, and I've taken a snip of the example and then pasted it into a notes page. Okay, so this is a notes page. So what you can do, the first thing that I want to emphasize tonight is that you can paste images into the notes page, so you can actually transfer examples from textbooks or even from exam papers and place them in notes pages so that you can do the example within the TI-Nspire environment. So in this presentation, the way I've set it up, I won't be leaving this environment at any stage. So the first thing we're going to do is just verify some addition properties regarding matrices. So we've got the commutative law for addition, we've got the additive identity and the additive inverse. And what we can do is we can verify those laws using a numerical example by saying, well, okay, let's let matrix A be 9, 4, negative 2, 3, and let matrix B be 10, 7, 2, negative 4. And then we're going to verify those following results. A plus B equals B plus A plus the 0 matrix equals A, and A plus negative A brings us back to the 0 matrix. So we move to the next page. This is a calculator page. Now, if you have a question or an activity where you're using matrices on a few separate occasions, it's a very good idea to assign them a letter or to store them as a letter. Now, in this environment, there is a mismatch in notation. So on paper, students will be using uppercase letters to represent matrices, but in this environment, we can't use uppercase, we can only use lowercase. So whenever there's a mismatch in notation, it's really important to be upfront and to mention it. So what I've done here is I've assigned those matrices as A and B respectively. The assigned symbol, as you can see, is colon equals, and that is obtained by pressing Control and then the symbols template. Okay. Now, what also would work is the store command, which is accessed by pressing Control and then var. Now, don't worry about the fact that it comes up as an answer there. What you would do is you would enter the matrix, then press Control var, and then store it as A or B, depending on what you're doing. So I very much encourage you to use the assign command. One trap that could catch some students is, rather than using the assign command, they use the equal sign, and that's different. The equal sign won't work, so please use the assign command, colon equals. It's a legitimate CAS command, and I think it's the best one to use. So we're in problem 2, we're on page 2, and we've got matrices A and B assigned. So we go to the next page, and I've already completed the calculations here. So it's just a matter of entering A plus B, and you get that matrix there, 19, 11, 0, negative 1. B plus A, you get the same matrix. And the other situation is you can enter A plus B equals B plus A. And what happens in that instance is you get each element in the matrix comes out as true. And I think that that's a worthwhile example showing actually that it's for a numerical verification, it's very nice to have left-hand side equals right-hand side and to have true in each element there in the 2 by 2 matrix.
Peter?
Going on to the next page, up the top there, there's some quite weird looking notation. You can assign the 0 matrix, and you can assign it to have a particular number of rows and a particular number of columns. I'll show you where to find this in a moment, but that inside that argument there, 2, 2, that's saying that we want a 0 matrix with 2 rows and 2 columns. So in other words, it's a 2 by 2 square matrix. So how you find that is to press menu, then number 7 for matrix and vector, and then under number 1, create, you will see there number 2 is the 0 matrix. And so that command will then be pasted onto the calculator page, and then all you need to do then is just fill in the dimensions, and in this case it's 2, 2. So that's quite worthwhile. Quite a trivial result here really, but still nice to see and to formalize, is that A plus the 0 matrix gives you a matrix A, nothing changes, and you can see that by again this left hand side equals right hand side verification, that A plus matrix O gives you matrix A. You again get those 4 elements that say true inside that 2 by 2 matrix. And following on from that, we've got A plus negative A. That takes us back to the 0 matrix. And again, left-hand side equals right-hand side. A plus negative A gives us the 0 matrix. True, 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 true. Okay. Another situation that may crop up, and it's a good idea to let it happen naturally, is you could ask the students with their matrix A, which is the 2 by 2 square matrix already assigned, you could ask the students to assign a matrix C, which is a column matrix. It's got 2 rows and 1 column, so it's a 2 by 1 matrix. So you can assign matrix C to be something like, say, 3, -4, and you can get them to experience the situation and then talk about the fact that when you attempt to add 2 matrices of a different order, on the Nspire, you do get a very useful error message that says dimension mismatch. And that is the error message that is displayed. So if I go, just type in A plus C and then press enter, you'll notice that you get more information. You get a dimension mismatch, and it then offers some more information that says 2 or more arguments must have matching dimensions. And that's why you've got a dimension mismatch, because you're trying to add a 2 by 2 matrix or form the sum of a 2 by 2 matrix and a 2 by 1 matrix. And they are of a different order. And that's why it doesn't work. So it's very important that students understand when particular matrix operations work and when they don't, and to anticipate when they won't work and to understand why they don't work. Moving on to our second part of matrix operation properties, and this time we will look at multiplication. And we've got the commutative law for multiplication that in general, matrix AB doesn't equal matrix BA. And we also have 2 distributive laws, the left distributive law and the right distributive law. So the left distributive law is matrix A times matrix B plus C is matrix AB plus matrix AC. And the sum of matrix B and C, B plus C, multiplied by matrix A is matrix BA plus matrix CA. And so this is also an excerpt from the Specialist Maths Teacher Resource book, which will be available to you soon. And this example, again, I've taken it as a snip from a PDF, from the PDF version of the book, taken the snip using the snipping tool and pasted it into a notes page. You can make it bigger by clicking on it and dragging that down. But what tends to happen in that situation is the letters and the text seems to elongate vertically. So that's why it's the size that it is. So we've got 3 matrices. You can already anticipate that they're going to be assigned as matrices A, B, and C respectively. And then we're going to verify each of those results in a very similar manner to the manner that we looked at for the addition example. So we go to the next page, and it's no surprise there that we've got matrices A, B, and C. They've all been assigned. And again, I want to make the point, the symbol there is colon equals, and it's found by pressing Control and then the symbols template. Okay. So we move to the next page, and we can have a look at a numerical situation and see whether the commutative law holds for matrix A and B. So we form the product AB and we get the matrix 98, 47, -14, -26. We also form the matrix BA, so we're reversing the order of the multiplication. We get a different matrix, 76, 61, 26, -4. Each corresponding element is different. And again, I do like this left-hand side equals right-hand side situation where we can say, well, all right, we see it, but let's look at the output when we type in A times B equals B times A, and each element inside the matrix is false. What's also very nice is to look at it from the point of view of not equals, but not equals. And in the case where A times B is not equal to B times A, we get a true for each element in that 2 by 2 matrix. To find is not equal to, the simplest way is to press Control equals, and you can highlight the not equals to symbol and then press enter, and that will paste it onto the new entry line. Let's look now at the left distributive law. And what you might notice, I'm in a calculator application, and at the top of the page, I have what's called here a comment. And the comment is saying, verifying the left distributive law. And I think that comments can be very useful in pre-prepared files that you might take into class and use with the students. They can be used as scaffold, they can be used as explanation, they can be used as instruction. And in this case, it's used as instruction. How do you put a comment onto a calculator page? Well, what you do is you press menu and then you press 1 or enter for actions, and then number 6 is insert comment. And what will happen there is you get that sort of copyright symbol, and then you can press I would encourage you to press the space bar, and then you can type away. You can type in normal text, normal sentences with capital letters, lowercase letters, and you can also type in numbers, and we'll see that in our last example definitely this evening. So again, we have, I've already entered in here, matrix A times matrix B plus C, and out comes the result. I have then typed in matrix AB plus matrix AC, and we note that we get the same matrix. And so it's a numerical verification of the left distributive law. And again, we get this using the left-hand side equals right-hand side established practice. We end up with each element saying true. Now, I won't go through the right distributive law. It's exactly the same process. And again, it's very important to say to the students that when we're establishing a numerical case, in teaching and learning, you don't have access, or if you don't have access to a CAS calculator, then what you can do is you can get the students to prove these results algebraically. It's nice and typical in these situations to offer a numerical example as a primer or a precursor to then producing or asking the students to produce a symbolic verification, symbolic showing the result, and if you want it to be even stronger in your language, a symbolic proof. Okay. When we deal with multiplication, we also come up with a potential situation for error. And so notice here on this page, I've used the comment facility. And so that's accessed again by pressing menu, 1 or enter for actions, and then number 6 for insert comment, which is that one there. Just pressing escape. And this comment is very important. It's saying that when attempting to multiply two matrices of a different order, a dimension error message is displayed when the number of columns in the first matrix doesn't equal the number of rows in the second matrix. So let's have a look at this in practice. Now, I'm in the same problem. This is problem 3, where way back in one of the early pages, possibly even the first or the second page, I assigned matrix A to be 9, 4, negative 2, 3. So within the same problem, all I've done there is I've typed in A and the output is the matrix, which is really nice. What I've also done here is I have assigned matrix D to be a 2 by 3 matrix with elements 1, 2, 3, 4, 5, 6. And what I'm going to show you now is how to construct a matrix that isn't square, one that is that has 2 rows and 3 columns. So if I come down to a bit of play space, to a new entry line, and what I can do is I can press the catalog button, and in row 2, what we have some templates. So there's the 2 by 2 matrix template, the 1 by 2 matrix template, the 2 by 1 matrix template, and the M by N matrix template. So we can't use any of these 3 because we want a 2 by 3. So with that highlighted, we press enter, and up comes a create a matrix dialog box. And what we can do is we can say, well, okay, we'll up arrow there, go down arrow, apologies. So the number of rows is adjusted to be 2, and the number of columns is 3. Now, I haven't introduced a letter. I'm just showing you how the matrix is created. You press tab down to OK, and then press enter. And there you see your 2 by 3 matrix template. So in constructing the line that I'm about to go up to again, what you would do is you would type in D, then control symbols template or the assign command, and then you would go into your catalog and you would work through the create a matrix or the M by N matrix template to form matrix D. If you notice there on the next line, what I've done here is I've now formed the product of matrix AD, and we've been able to get matrix AD. Matrix AD exists, and it can be found because matrix A is 2 by 2, 2 columns, and matrix D has 2 rows. 2 equals 2, and therefore matrix multiplication works for this situation. However, when we come to reverse the product and look to calculate matrix DA, so for example, if I come down here and I type in D, just as an aside, this is a good sign. When the letter is bold and non-italicized, what that means is that we have something stored or assigned for D. If that was just a normal italicized D, then it's a chance, for example, we may have used the equal sign. Use the multiplication symbol and then A, press enter. And what comes up is a more detailed message. It certainly alerts us to the fact that there's a dimension error, there's a problem, and a list or matrix index is not valid. It then gives an example. So we press OK to get out of that. Just go up and press backspace to delete it. And what we can conclude, and so this is well worth discussing with the students, and it's also well worthwhile doing it in a semi sort of experiential way, is that matrix DA cannot be found because D is a 2 by 3 matrix and A is a 2 by 2 matrix. So number of columns is 3, number of rows is 2, and 3 doesn't equal 2. Okay, so it's crucial that students understand the conditions for which matrix addition, and obviously I know I haven't talked about it this evening, but a matrix subtraction, and also matrix multiplication, the conditions for which these operations work. Okay. Moving right along, we've got a very brief example here on the multiplicative identity and the inverse. So again, I've got a 2 by 2 square matrix for matrix A and a 2 by 2 square matrix for matrix B. And I've been quite clever in my choice for matrix B. We're going to verify these results very quickly because I feel as though that you can anticipate what's going to happen. But we're going to quickly verify that when you take a matrix and multiply it by the identity, you still get the original matrix, and it doesn't matter in which order whether it's post-multiplied by the identity or pre-multiplied by the identity, you still get that original matrix. But what I've been quite clever with is showing here that matrix AB equals the identity matrix, which equals matrix BA. And if that's the case, we can conclude, therefore, that B is the inverse matrix of A. And that will give you, there'll be a clue to that in this sense, because we've got a scalar out the front. And of course, that's going to be linked to the determinant, which we'll show you just in a moment. So again, this is an image from the Queensland Specialist Maths Teacher Resource Book, taken a snip using the snipping tool and copy and paste and put it into a notes page. You can also, it's quite a trivial sort of comment I'm about to make, but in a notes page, you can also write text. So there we've got the heading. What I'm going to show you in an example coming up quite soon is you can actually also perform calculations in a notes page. And the notes page environment is the least well known of the applications, but it's also the most powerful, I feel. So moving along, notice that I've changed problem again. I'm in problem 4, page 2. So when you can probably get a sense of what I'm doing is that when I'm changing topic, changing example, I'm adding a new problem. So if I press doc, you can see here under number 4 for insert that I can choose to insert a problem, or I can choose to insert a page. Notice that the page comes with a shortcut Control I, and the I stands for insert. Notice also that Control Doc also allows you to add a page. Might be hard to see, but in red above Doc is a plus page. It's in quite small type. And my feeling about problems is whenever you start a new question, always start a new problem, because what the new problem feature does is anything that was assigned in problem 3 is not applicable or is not recognized in problem 4. So if I had a matrix A in problem 3, it's not recognized in problem 4. And that's why here I've assigned matrix A again to be 5, -4, 2, -1, as you see there. Matrix B assigned. And for square matrices, the way I do it is the catalogue, and then you've got that easy to access 2x2 matrix template there. What you'll also notice is that you can very quickly get access to, and in this instance, assign an identity matrix. And it's the one, of course, very important one, where you've got the ones on the leading diagonal of a square matrix and zeros on the non-leading diagonal. This syntax, I'll show you again in a moment where you find this. I've assigned matrix I to be the identity matrix, and this number here is basically saying we want a square matrix that is of order 2x2. So the 2 is representing the number of rows and the number of columns. And again, if we press menu, press 7 for matrix and vector, a very popular menu is the create menu. So if we press 1 or enter, notice here that if we scroll down to number 3, below the 0 matrix, we've also got the identity matrix. And so you press enter to paste that into an entry line, and then all you need is to put in a number, and then that number will determine the order or the dimensions of the matrix. So if I press enter here, and I put in 3, there we go. We get the identity matrix for the 3 by 3 case. Okay. So very quickly, again, matrix A times the identity matrix gives you matrix A. Matrix, or the identity matrix multiplied by matrix A, again gives you matrix A. And again, I like this left-hand side equals right-hand side situation, and each element in that matrix is true. Moving along, the second example there was, now I've set it up so that A and B are inverses of each other, so it's no surprise that when you form their product in either order, you end up with the identity matrix again. So, and that's shown in those last two entry lines again. Okay, so you take a matrix, you multiply it by its inverse, it takes you back to the identity matrix. So really, we're starting to talk about group theory, but not really formalize it just yet. Moving on from that, we've got two examples now on determinants and inverses. And the first one concentrates quite strongly on determinants. So I've got a more involved question here. We've been given a Fibonacci sequence which has been defined in this particular way. So to generate a term of a Fibonacci sequence, what you do is you add the two previous terms. And the way I've set this up is I've said that F1 is 1, F2 is 1, F0 is equal to 0. We need that for when we look at these matrices. These matrices are very closely related to the Fibonacci sequence. They are from a family of Fibonacci matrices, and we're looking at the Fibonacci matrices from a 2 by 2 perspective. And we're saying here that n is greater than or equal to 3. So those last two conditions really help us in setting up the problem when we come to looking at determinants and matrices of various powers of this matrix P. So the first part of the question asks you to determine the terms in the Fibonacci sequence F3, F4, F5, and F6. So really, it's quite straightforward to see that F3 is just going to be 1 plus 1, which is 2. And then F4 is going to be 1 plus 2, which is 3. And similarly, F5 is going to be 5. And F6 is going to be 8. So those first 4 terms there in part A that we've been asked to determine are 2, 3, 5, and 8. You can go into a lists and spreadsheet page and use the generate sequence command with those initial conditions to generate many terms of the Fibonacci sequence, but we won't concentrate on that tonight. How you do that, however, is shown in the Queensland Specialist Maths Teacher Resource Book. And again, this is an excerpt from that. So we've been asked to consider a 2 by 2 matrix P, which has elements 1, 1, 1, and 0. And what we're asked to do, if you have a look at the question as an overview, is we're asked to find matrices of P that have been raised to a particular power. So we've been asked to find P, P squared, P cubed, and P to the 4th. And also we've been asked to find the corresponding determinants of those matrices. We're then asked to have a look and see, can we deduce, or infer is a better word, a pattern and a general result for the general matrix P to the power of n and the determinant of P to the power of n, and then see if we can use the result from part D to find an expression for, and this is a well-known Fibonacci identity, that if you take the product of a term in the Fibonacci sequence and multiply it by a term which is 2 back, and then subtract or minus Fn all squared, you get a general result every time. And that also can be proven via induction. It's really nice here to see an example that links up various parts of mathematics. So you've got the possibility of an induction proof. You've got a lovely identity which will emanate from the determinant of this general matrix. Now, you may not have seen this environment before in this guise. This is a notes page, but it doesn't have, well, it does down the bottom. I can just see it does have an image that has been snipped from a PDF, but it has a number of other different objects. It has what's called a slider for n. This slider, what it does is it controls the value of n. So I've written here slider for n, so that's being used as text to explain what follows underneath. And what we can do is to insert a slider. What you would do is just up here and press menu, number 3 for insert, and then number 5 for slider. And what happens is the slider settings dialog box appears. And so what you would do is you would type in your variable. So for example, n would be the one you would type in there. Have a current value of 1, minimum value of 1, maximum value of whatever you like. I've got it as 5 here at the moment. In the actual slider, I think I've got it set to 10. The step size, I would consider all you need to do is just change that and enter a value and enter 1. All right, so enter a value and just enter 1. I'm not going to press go all the way through and press OK. If you remember the display of this slider, it looks like 2 buttons that you can click on. And the way that you get the slider to display like that is to check. So you can press the center of the navigation pad to check the minimized field there. And then you would tab through to highlight OK. All right, so tab through to highlight OK, and then you would press enter. So that's how you set up a slider, quite straightforward. What I've also done is these objects look, well, familiar in one way, but mysterious in another. These, if you click on them, which I'm clicking on them now, these are called math boxes, the American term. In English, it's called maths boxes. So if I end up interchanging between those two terms, I apologize. Notice here that I've assigned P to be 1110. The input is in blue. The output is in green. Now, the question is, how do we insert a maths box? Now, I'll come up into clear space here, and I'll press menu, 3 for insert, and you'll see here I've got it set to UK English, so it says maths box. And also notice that it comes with a shortcut, Control M. So if I pressed Control and then M sequentially, a maths box would appear. So if I press enter, there is an example of a maths box. Okay, so you've got a dashed inside border that's in black, and then you've got a red dotted border outside that. When you're working with math boxes, it's really important to make sure that you keep cognizant of where your cursor is. So if I go arrow to the right, I'm out of it now. So, you know, if I'm blissfully typing in P and I want to assign it as that matrix, it's not going to work because I'm not inside a math box. It will work when I'm inside that math box. Okay, so that's how you insert a math box. Just press backspace there to delete that. So the other thing you need to be aware of is inside, you press menu, and to find all your various menus that are in the calculator application, you have to dig a little bit further. And so what you do is you press number 6 for calculations, and they all come up. So you'll be familiar with all this. Included in this, for example, is number 7, matrix and vector. And there we have all the matrix and vector commands and the create submenu there. All right, so that's how you get access to all your assets, all your functionality from the calculator application. They're all available to you here in the notes application. The other thing I might say is to add a notes page. It might be worthwhile just mentioning that. I'll just come up here. We won't end up using this page, but if I press Control Doc, I could have pressed Control I. Notice that number 6 is add notes. I press enter, and I've just added a notes page. I say to myself, well, okay, I don't want that notes page. What you can do is you can press Control and then the navigation pad up. And what happens is you get an overview of the document. So you can see here that I've named this problem Determinants and Inverses 1 for part 1. This was the page that was alive. It's surrounded by a blue border. And if now I'm on a computer, so I'm going to right click, but if I press Control menu on the handheld, it will say, do you want to cut, copy, delete, move? I want to delete. So that's a quick way to delete the page. Okay, so I'm hopeful that you can be able to assign matrix P. Always press enter. So blue is input in this instance. You can change the color, but I'm not going to bother changing the color. Coming down here, what you might notice is that we have an arrow in that math box, but we have an equal sign in this math box. And what you can also do is you can change the appearance of a math box. So I'm inside a math box, and if I press Control menu, which is right click, go to math box attributes, what you can see there is you've got your various fields. You can press tab, and so insert symbol. If I press navigation pad to the right, then I can choose the arrow, the equal sign, the not equals to, etc., etc. So that gives you a very quick view of how you change MathBox attributes. And the other thing here is another MathBox with the determinant. How do you find the determinant? Command. What you do is you press menu, then 6 for calculations, 7 for matrix and vector, and then number 3 for determinant. Okay, what's lovely about these math boxes and this slider is that they are all linked. So when I click on the button to increase or to change the value of n, what you will see is corresponding changes in p to the power of n and the determinant of p to the power of n. So if I click on it and go to n equals 2, n equals 3, what you'll notice is the determinant value is toggling. It's toggling from -1 to +1. And what you'll notice with the elements in p to the power of n is that each element forms or is part of the Fibonacci sequence. So for example there, for n equals 4, we can see that this is F5, that's F4, that's F4, and that's F3. And so by noting that, we can get an understanding of the pattern as we go through there. And if we come down to this snip, because of time, I'm just going to sort of quickly cut to the chase, that what you would get the students to do is to infer the general result that p to the power of n is a 2x2 square matrix, and the elements come from a Fibonacci sequence. F of n plus 1 Fn, Fn, Fn minus 1. And the determinant, which is changing sign and toggling from -1 to 1, can be expressed as -1 to the power of n. And what you'll also notice is that if we look at the determinant of matrix p to the power of n, the product of Fn plus 1 and Fn minus 1 minus Fn all squared, that's the determinant for p to the power of n. This is the determinant for p to the power of n. So we have beautifully been able to determine a fundamental identity of the Fibonacci sequence. And we would then say to the students, if they had the experience and they knew about induction, can you now prove this using induction? So what I strongly urge you to do is when you're raising matrices to a power and you've got an activity such as this where you're asking students to generate cases very, very quickly and to infer a general result, the notes page is very much your friend, because you can see the results appear live and it makes for inference, I think, a lot easier. Moving right along, just looking at the time, what I will finish up with is a quick look at determinants and inverses, part 2. We'll show you how to use the inverse matrix to solve a matrix equation. So matrix A is that 2 by 2 square matrix. Matrix B is that column matrix. And we want to form the equation AX equals B. The solution to that is that X is equal to the inverse of A multiplied by B. Yeah, so what you do is you pre-multiply both sides by the inverse of A. And again, I'm on a calculator page. I have assigned matrix A and matrix B as shown. For matrix B, for example, you press the catalog button, scroll across, and there's your 2 by 1 matrix template there. So it's just a matter of pressing enter and that pastes it in onto a new entry line. So with those two matrices assigned, then what you can do, that's just a simple case of taking matrix A. So you type in A, and then you simply just raise it to the power of -1. That's all you do there. And that gives you the inverse. And then it's just a matter of you take that inverse of A, multiply it by B, and you get the column matrix there, 13, 14. And so therefore, that is the solution to that matrix equation. So matrix X is equal to that column matrix there, 13, 14. And you can verify there that you take a matrix and multiply it by its inverse, you come back to the identity matrix. Okay, we're in our last example now, so thanks very much for watching. I'll show you 3 different ways of solving a system of linear equations, which ends up being a 2 by 2 matrix system of equations. So we want to solve that system of linear equations, -2x plus 3y equals -19 and 5x minus 2y equals 20. I've offered 3 methods here. Of course, you can also use the inverse approach, and I've already shown that, so I won't show it in this example. This first one is quite intuitive. The second one is quite mysterious, but it works, and it's probably the one students should use in the exam. And the third one is an acquired taste and it does take a couple of minutes, well, to explain and also to understand. So let's have a look here. Let's look at the reduce row echelon form command, and where that can be found is if you press menu, 7 for matrix and vector, and you can see number 5 there is reduce row echelon form. And so you get your ref command there. So I have matrices A and B assigned, and they come from the system of two equations in two unknowns. What you can do is you can bring those matrices, you can bring them together so that you've got the 2 by 2 coefficient matrix and also the coefficient matrix in the 1 2 by 3 augmented matrix. And you do that using the augment command. So you press menu, 7 for matrix and vector, 1 or enter for create, and then number 8 for augment. And if you augment, the syntax is first matrix, comma, second matrix, and the comma's found down there below the pi. You can see that you're able to augment or combine the two matrices, as I said. What reduced row echelon form does is it performs elimination for you so that you end up with a transformed augmented matrix. It's equivalent, but it's been transformed into, rather than negative 2x plus 3y equals negative 19 and 5x minus 2y equals 20, it's now 1 times x plus 0 times y equals 2, and 0 times x plus 1 times y equals negative 5. In other words, we can look at this augmented matrix and say, we've found the solution. The solution to this system of equations is x equals 2 and y equals negative 5. Just remember this matrix, because this is going to be important when we come to look at our row operations. Using the simultaneous command, this is very mysterious. It's very black box. You press menu, 7 for matrix and vector, and then number 6 for the simultaneous command. And then it's just a matter of typing in A, comma B, as I've shown there in the previous entry line. And this output is simply saying the solution to this system is x equals 2, y equals negative 5. Now, the final one, and of course, as is tradition, we leave the fiddliest thing to last, is we're going to perform row operations starting with that augmented matrix, and we're going to do these row operations manually. Now, the goal here is we want to change this augmented matrix via a series of multiplication and addition of rows. In other words, row operations. We want to change it so that you've got in your, let's say, the 2 by 2 bit here, you've got 1s on the diagonal, they're called pivots, and 0s on the non-diagonal. So this is the goal. And again, I'm using the comments feature here. And so what we want to do is we want to say, well, okay, how can we get a 1 in that position? So we're saying, let's multiply row 1 by negative a half, and that becomes our new row 1. So in other words, we're going to multiply row 1 by negative a half. Now, where you find all these row operation commands is if you press menu, 7 for matrix and vector, and then 9 for row operations. You can swap rows, you can row add, you can multiply row, or you can multiply row and add, and each one of those has a specific syntax. And the syntax does take a little while to get a handle upon. So here is what I've done. So I've accessed the multiply row command. Just want to make sure that I'm saying the right thing. Menu, matrix and vector, row operations, multiply row command. Go back to this. This is so our first, they're comments, and this is a calculation. So multiply row. This first number is the multiplier, so that's negative a half, comma, the matrix. So I've just typed in augment A and B, and comma, and this 1 is the index, and it denotes the row number. So we perform that row operation and we've achieved our goal there. We've got a 1 in that position of the augmented matrix. What we want to do now is we want to work on row 2. So we say to ourselves, well, okay, why don't we take -5 times row 1 and add that to row 2, and it becomes the new row 2. We want to get a 0 there. So we multiply row 1 by -5 and add it to row 2. So this is a composite. So this is a multiply and add. So this is multiply row and add. So you get it from the same place I showed you for multiply row. -5 there, that's the multiplier, comma, the matrix. Now, comma, index 1 is the row being multiplied. So that's row 1. And index 2 is the row being added to, right? So that's row 2. And when we do that, we've achieved our goal so far. We've got a 1 there and a 0 there. So what we want to do, we've got to keep the goal in mind here, is we want a 0 there and we want a 1 there. So if we have a look there, we can say, well, okay, why don't we take row 2, multiply it by 2 on 11, and that becomes our new row 2. So we use the multiply row command. Our multiplier is the first number. The matrix, the augmented matrix we're operating on, is the second argument there. And the index there is the row that we want to alter. So multiplier, matrix, and the row. And so we've got a 1. It's looking quite a bit better. We've got a -3 on 2, 0, and a 1 there. So then we say to ourselves, well, okay, why don't we take row 2, multiply it by 3 on 2, and add it to row 1, and that becomes row 1. So that's what it is in words. Then we grab the multiply row and add command. So we multiply by 3 on 2. We operate on that matrix. We want to multiply row 2 by 3 on 2, and we want to add it to row 1. So that's why the indices are in that order, 2, 1. And what comes out is our reduced row echelon form matrix, 1, 0, 2, 0, 1, 5. And we now know to read that off as the solution to that system is x equals 2 and y equals -5. So that completes my presentation this evening. If I just go back quickly to the outline, I just wanted to show you that I wanted to illustrate ways in which you can illustrate and numerically verify some matrix operation properties. Also do the same for the identity, multiplicative identity, and the multiplicative inverse. Show you how to work with determinants and inverses. Show you how to solve systems of equations and matrix equations using various features of the TI-Nspire. And also I wanted to introduce you to the notes environment, the notes page environment, which is really, really useful for investigations where a number of cases, you want to generate a number of cases quickly, and then you want to generalize from that and then do a proof. So thanks very much for your attendance, and I'll now hand back to our host, John. So thank you very much.
Fantastic. Thank you, Peter. Thank you. I have to say, using the notes page is a fantastic little feature, isn't it?
It certainly is. Yeah, couldn't agree more. It's the I may have said it in transit there. It's the most. It is the most powerful, but it's also the least well known. And I'd certainly encourage teachers to become familiar with it, because you can bring together sliders, images, and the various calculations. So it's a more powerful and more versatile application than the calculator application. So yeah, thanks, John.
Oh, it was great, and I love the bit about the row operation approach, an acquired taste. I was following along thinking, yeah, I'm definitely getting an acquired taste, and I think some students would love that methodology.
Yeah, the good thing about it is that the calculator will give you feedback, so you can, what I showed you was row operations, they all worked. But if you let students have a go at them themselves and they, might make a mistake, they could have a chance to consider how they might change their row operation and maybe learn from it. So, because they get feedback all the time. So, that is one positive. But I would like to make the point carefully that it does take a while to get used to those row operations and the syntax.
Yeah, you're right. But the syntax does make sense. And obviously, we can always find it in the catalog if they scroll down through there and look for the individual one.
Yeah, good point.
Right. All right. Well, we better start finishing up. So just wanted to remind you that our dedicated Queensland TI education page can be found at education.ti.com/AUS/QLD. And if you scroll to the bottom of the page, you'll find the downloadable teacher resource ebooks like the one that Peter was using tonight. And although he mentioned that it will be available soon, it's there right now. You can see it on my screen, the QCE Specialist Maths Teacher Resource Book. Only available as an ebook at the moment, but printed copies will be available, so I'm told, from about April. We're going to begin wrapping things up. So if you have any last minute questions, please try and get those asked, as I know Peter will endeavour to answer them. Or equally, we can add them to planning of future webinars. And when you leave this webinar tonight, a brief 4-question survey will automatically appear in your browser. Your feedback guides us as we plan future online events. We listen to your feedback, and so we hope you share your thoughts in a post-webinar survey. And if you're watching live in the next 24 hours, you'll be emailed a link to the past PD events. I also encourage you all to check out our student, or teacher for that matter, online courses in our very own TI dedicated YouTube channel. And sadly, that brings us to the end of our webinar. Thank you, Peter, for everything that you've shared with us this evening. I've really appreciated it. I know that our viewers have too. So thank you very much, Peter.
Yeah, thank you, John, and thank you to the people who attended. Thank you.
Yeah, very much indeed. We run these webinars for you, either to watch live. So thank you for those that joined us this evening. It was great to have you with us and your comments that you added. And also, if you're watching it on demand, thanks for tuning in. And I hope not only that you learn something from it, but that that knowledge is then shared with the students and they become better mathematicians. So everyone, thank you very much and have a good night.
Yeah, good evening all.